back, get registered. Yeah. Are you coming back or are you graduating?
I'm out.
He says with a big grin, right? All right. So I had mentioned before I had started the recording that we have 3 basically lectures left. We're going to, well, we have 4 including today's. We're going to finish up chapter 8 today, and then we'll go ahead and do chapter 9, and I'll do an overview of Project D as well. I imagine I'll either do that on Tuesday or I'll just record the lecture. How long it's going to take me to cover the chapter 9 material to make sure we'd have time to do that in class. And then after that, it's about the on-campus folks are going to meet during finals week, and we'll do presentations then. And I would anticipate your presentations not taking more than 10 or 15 minutes each, so shouldn't be any problem to get through that during our finals block. And then my online students need to make an arrangement with me to meet, and we'll find a space online to meet. And basically, you'll be able to go through your PowerPoint, and we'll be able to hear each other back and forth. I won't necessarily, not really going to make it where I have to see you, but I want to be able to at least hear you do the presentation. So I'll put out a schedule of times that are available, and then you'll need to go ahead and select a time from that schedule. All right? So we did a little bit on this lecture. We were talking about the exponential model, and I had an online student tell me I didn't have these slides out there for the online students, so they are out there now. I think they were available for the on-campus students. I just didn't get them posted in the online section. I have to tell you, every year I have to go back and review what a Poisson arrival means. And basically, it's a statistical approach to saying that you have this space and that you're picking a particular point from that space. And so what we're saying is that we're randomly picking those points from space. And so it's this infinite pool of potential arrivals who arrive completely at random, and they're independent of one another. And it's an average rate of R sub I, which is constant over time. Okay, and then our exponential processing time is also completely random and unpredictable and independent of the arrival time, right? And during processing, the time remaining doesn't depend on the time elapsed, okay? And it has an average mean of time of processing of T sub P, okay? All right. And so what we know about that is our coefficients of arrival time and coefficients of processing time when we assume a Poisson arrival and exponential processing times are 1. So therefore, we can kind of change our formula a little bit. So last time we looked at the inner arrival formula, and we ran through one example, and we said we could see how we could do the second example with 1 server and 2 servers, right? And so when we had 1 server, our utilization rate was 83.3%, right? Our safety capacity was 0.033, right? Our I sub I, which was 4.162, which means that we had on average 4 people waiting. So the I sub I relates to on average, the number of people waiting, okay? That T sub I is 0.416, and again, we're doing this in minutes, so it's 0.416 minutes, and that's the average time that someone is waiting. Okay, total T is 0.499, and what we said is we can figure what the processing time is then by taking the 0.499 minus the 0.416, because we know that for both time and inventory we have 2 components. We have people that are waiting for inventory, and we have people that are being processed, and you sum those together and you've got the total people in the process. Same approach on time. We've got the average time that it takes for people to wait and the average time that it takes for people to process, and you sum those together and you've got the total time in the process. Okay? All right, and then we went ahead and said, okay, well, what if we added another server? How does that change things? Well, our server, of course, our utilization is cut in half, right? Because now we've added another server. Our safety stock goes to a 0.233, right? We significantly reduce the number of people that were waiting in line. We significantly reduce the amount of time that they had to wait. So again, that goes back to that trade-off conversation, right? So my utilization goes down. So from a cost perspective of servers, right, that's more expensive because I'm not using my servers as efficiently. However, my customers are having to wait a lot less. So therefore, what's that trade-off, right? And so that's some of what we're going to talk about today is how do we calculate where that sweet spot is, and that's what you're trying to find, okay? So when we're trying to improve our performance, we can look at capacity utilization and our safety capacity, right? So I can think about my arrival rate, peak load pricing. I can increase the capacity. I think we talked about this on Tuesday as well. The variability reduction, I can look at how can I take variability out of the arrival times, how can I take variability out of the processing times, and how can I synchronize and match my capacity with demand, okay? So up to this point, we've been assuming that infinite capacity, right? That you can just have people get in line for however many, right? And what we talked about on Tuesday is that sometimes we have a finite capacity. If I have a call system where I only have 5 telephone lines, right, and I have 1 server, my buffer capacity is 4, and I have the 1 server, using the 1 line for the actual customer call in. If I increase that to 2 servers, my buffer capacity goes down to 3 because now I have 2 phone lines being used for actual service and 3 being used for waiting. Okay, and so just from a variable standpoint, K is the buffer capacity. Capital K represents the buffer capacity, and you get that by, if we're talking about telephone lines, the number of lines minus the number of servers, right? That's how we get that. All right, and so we could go through and use our performance.xls spreadsheet, and that's what we're going to work on today, is how do we use that spreadsheet to fill in this information that then tells us if I move from a buffer capacity of 4, which would mean if I had 5 telephone lines, I had 1 server, a buffer capacity of 5, a buffer capacity of 6, how does that change how many people are waiting? How does that change how much time they have to wait? How does that change the probability that they're going to be blocked, right? And how does that change our processing rate and our utilization, okay? And so we talked about that there were these 4 approaches, or these kind of 4 pieces of information if we're going to try to talk about the total cost of these capacity decisions. And the first one is, what does it cost us if we lose the business? So if they're blocked, and so whenever you see that sub B, we're talking about somebody being blocked from the system, okay? What is the buffer capacity cost? Because as I add more telephone lines, right, there's usually an additional cost for each line that you're going to add, right? There's a cost of waiting time. We know that for customers that have to wait on the phone for a longer amount of time, they purchase less, okay? And so we can calculate that. And then what's the cost of processing? So if I want people to have to wait less, I'm going to have to add more servers potentially. So if I add more servers, what's the cost of that? And so what we have to do is kind of look at a way to figure out what's the best trade-off amongst those pieces of information, okay? All right. I think what I want to do is go ahead and go over to some examples from the textbook, and we'll talk through some of those examples. The first thing I want to do is I want to introduce you to this performance.xls spreadsheet. Sure I do. I want it to stay up there so I can introduce it. All right, and what you'll notice is that it has these instructions, which we're going to walk through how to use it, but it's always going to open up to this. And then we have a tab that says infinite queue and finite queue. And so the very first decision when you go to use this is, are you dealing with an infinite line or one that has a limited capacity, okay? And so if you're dealing with an infinite line, right, we have to know 3 pieces of information in order to be able to use the spreadsheet, okay? We have to know how many servers we have in the system, okay? We have to know what the arrival rate is of our customers, and we have to know what the processing rate is of our customers. And you have to make sure that these 2 are in the same unit of measure, okay? Because that's kind of It's kind of a kicker. So if I were going to go to the first example that I wanted to go through, I think it's 8.6, but let me just... Okay, so 8.6 is kind of similar to what the example that we were using before when we were manually calculating it, okay? But right now what we're going to do is we're going to use this spreadsheet to run those calculations, okay? And so you know how we kind of set that up, and we ran kind of the two columns to do the coefficient of arrival rate and the coefficient of processing rate, and then we substituted it in for numerator and denominator, and then multiplied them together, and we came up with our happy answer, right? So this is how another approach to do it, okay? So in that example, our average passenger arrival rate, R sub I, okay, and for whatever reason, this spreadsheet will do this occasionally, and you just click OK, okay? So we know it says our average passenger arrival rate is 10 per minute. So I'm going to go ahead and put in 10 into the spreadsheet. Okay, and the average processing time of T sub P is 5 seconds. So right away, what's my problem? My arrival rate is 10 per minute, and my processing rate is 5 seconds.
They need to be in the same measure.
They need to be in the same unit of measure. So if I'm going to convert that, so 1 over T sub P is 1 over 5 per second, right? And if I then multiply that times 60 seconds per minute, that's going to change that. So that then becomes 12 per minute, okay? And what I can show you is we know that that's a stable process, right? Because our arrival rate is less than our processing rate, okay? And so whenever we're working with this, that's one of the things that we want to kind of look at, all right? And with one scanner, the number of servers is 1, okay? And then it gives us this information, and I can just start to go down and I can go, well, the average amount of people in queue is 4.1667, right? The average time that they're in queue, that they're waiting, is 0.41667, and you have to remember your unit of measure is in minutes, right? So we want to make sure that we answer that in minutes, okay? And my average server utilization is 83.33%, right? And so again, you know, we ran through that manually on Tuesday, right? And just by knowing those 3 pieces of information, the performance.xls is going to give us that information. And we just need to be able to know where to go to read it off of the spreadsheet, okay? And then it's going to tell us that the average number in the system, the total inventory is 5, right? And the average time spent in the system is a half a minute, 0.5 of a minute, okay? And the thing to remember is I sub I is our inventory where? What does I sub I represent?
The number of people waiting.
The number of people waiting, right? And I represents the number of people in the entire system. So if I needed to know the number of people that were in processing, how could I get that? What's that relationship? I know the total number of people in the system is 5, right? I know the total amount of people that are waiting is 4.17.
You just take 5 minus that.
Yeah, so the average number of people in processing is going to be 5 minus 4.17, right? So again, it's just understanding what those relationships are. And that is the same relationship that you're going to have with time, right? So if the average amount of time in the system is 0.5, right, and the average amount of waiting time is 0.41667, the average amount of processing time is going to be 5 minus 0.5 minus 0.41667, okay? And so what I want to do is I want to go to and so basically what I've done is I've copied that information into this spreadsheet so that we can just take a quick look, okay? And so what we've done is this is what we calculated with performance.xls, right? And so I can change that real easily to 2 servers, sometimes 2, right? And then I'm going to get this information, right? Average waiting in queue, 0.17507, average time, 0.01751 minutes, right? And so what I'm going to do is I'm going to transfer that so that we can just kind of look at that comparison, right? So here's that information that we get from performance.xls in minutes. Here's where we change that to seconds, right? And here's what we had from example 8.4 when we manually calculated it in seconds, right? And so the whole point of kind of walking through that in those 2 formats is to say, using the formula, right, versus using the spreadsheet, what are the differences? They're qualitatively similar, right? While the exact information is slightly different, they're qualitatively similar. And what we want to recognize is that in 8.4, right, so that was when we manually calculated it, we permitted arbitrary probability distributions of inter-arrival and processing times, right? And we used the Q-length formula to calculate that. In 8.6, we obtain more exact results, but we have to assume that exponential distribution for inter-arrival and processing times. And basically, that's a better statistical assumption to move forward with, okay? So, if you don't have this spreadsheet to work with, using the inter-arrival formula gets you qualitatively close, but this is a better approach in terms of getting better results, okay? And it's quicker, right? I mean, it's a pretty handy tool. Okay, so we conclude by just emphasizing that the Q-length formula that we did on Tuesday is exact only for the exponential model, and that too only for one server, okay? All right. So let's kind of keep moving and let's say, well, what else do we, want to look at? So I'm going to go ahead and open up the performance.xls and let's look at another example. Okay. So example 8.7 says, suppose that the call center is currently staffed by only one CSR who takes an average time to process of 2.5 minutes per call. Okay, so that would mean that her so as I'm going through this, so what information did I just give you when I said we only have one CSR? One server, right? And then when I said it takes them on average to process a call 2.5 minutes. So I can get the service rate from that, but I have to take the inverse of it, right? So I'm going to take 1 over 2.5 minutes, and that's going to give me 0.4 minutes. Okay, and then what you see is it says, wait a minute, your model is no longer stable, right? So it's not liking that. But that's because we haven't actually adjusted the arrival rate yet. Okay, and so then it says, with the number of servers being 1 and the processing rate, and it says 24 per hour, right? And we have 0.4 per minute. So we can either convert to hours or we can keep it at minutes. So let's kind of keep reading. And it says, suppose customer calls come in at on average of 3-minute intervals. So the enter-arrival rate is 1 over 3 minutes. Okay, so I can either go 0.333 here, right? Or I can take each of these times 60 and do it in an hour, whatever makes the most sense. Okay, and I think that they are primarily talking about per hour, so that's going to be 20 per hour as I take that times 60, and if I take 0.4 times 60, that's going to convert to 24 per hour. Okay, and so it's about just making sure you can calculate those 3 variables, right? In an infinite, you just have to know what those 3 variables are. All right, so Troy, what's the average time that somebody waits in the system?
0.208 hours.
0.208 hours, right? Austin, on average, how many people are waiting in the system?
4.16.
Yep. Okay. Abby, how many people in total are in the system?
5.
5, right? And Miranda, what's the average total time spent in the system?
0.25.
Of an hour.
7. Sorry.
That's okay. And I just do that because that's sometimes the common mistake that people make is that we just don't get the unit of measure right. So you need to make sure that you're kind of carrying that through. Okay? And so then I've got this information, right? And so what I do is I transfer it into the spreadsheet that I'm working on. Okay? And so to analyze that information, right? So this is how we did the conversion, right? And so to analyze that problem, we can input various numbers of servers and then calculate the associated costs of the servers because we understand what the goodwill is. And so here's how we do that. So we know that it costs us $20 for each server that we have. We're given that in the problem. So I set up this table to say, well, I'm going to evaluate across 4 different servers, right? And so what I know is, as I evaluate across those 4 different servers, every time I add a server, it's an extra $20 an hour, right? And here's why we probably want to do our spreadsheet in hours, because we're going to do our analysis in a cost per hour. Okay? So for one server, $20, $240, $360, $480, right? But it also tells us in the problem that we know, let me find the spot where it talks about the goodwill, that they lose $2 in sales for every minute that a customer has to wait online. Okay? So if I'm on the phone and it's $2 for every minute. So what's that cost per hour? 120, right? And so in order to determine that cost, I'm going to take, okay, on average, how many people do I have on hold, and multiply that by the cost per hour, and that's going to tell me my cost of those people having to wait. So I'm going to come back to, maybe I can do this, right? And there's a side by side. Let me see if I can figure that out here. It might be worth it if I can figure it out here. Apparently I can't.
And drag the window to the far corner. Either corner.
What's that?
If you drag it to the, like, if you take the window and drag it all the way to the far corner, it'll, like, go all the way to the left.
I can manually do it, but there's a way to do it. Okay, so what I'm going to do here then is I'm going to say, well, so at one server, what's my inventory? What do I need to put here? 4.16667, right?
Mm-hmm.
Okay. And so what that tells me then is that my cost of goodwill is basically $500 an hour. That's how much I'm losing because they have to wait on the phone if it's a $2 a minute cost. Okay. And then, sorry, I'm getting crazy. And then I can come back over here and I can say, well, what if I have 2 servers? Okay. Well, then I just update my I sub I, and it's 0.17507, right? And so now that reduces it to $21 an hour, right? So that's pretty much worthwhile to add that second server, okay? But if I add 3 servers into that equation, right, then my I sub I, so my I sub I represent how many people on average are on hold, is 0.0222. So it's $2.66. So now my cost is actually starting to rise again. So it's $62.60 an hour versus $61.01. So already I can tell you I really don't need to evaluate the 4th server because this is my lowest cost option, right? But let's go ahead and do it just because, right? And so now my inventory, again, my I sub I representing the people that are on hold is 0.00290, right? And so then I can get the cost of that for having 4 servers. And I can make a rational decision about where it's in the best interest of my company, how many servers should I actually try to have on hand, okay? Then on the next page, what they suggest with this same example is, well, there's two ways to look at this, right? One is I can look at it based on the average time that someone waits, or I can look at it based on the average time that somebody's in the entire system, right? And so you have to understand how you've calculated the cost that you've got, because that's going to make a difference in terms of whether or not you're looking at only the people that are on hold, or are you looking at all the people in the entire system. Okay, and so alternatively, LL Bean may be concerned with the total turnaround time that a customer spends for the entire transaction, including waiting for a CSR and being served. In that case, the problem is to determine the number of servers that minimizes that. And so if that's the case, I would start again, right, with one server. But what's the inventory that I would use? I wouldn't use the 4.1667. What would I use?
The total amount, so it'd be 5.
Yep, I'm going to use the total amount, so it would be 5, right? And so then, that basically changes the cost slightly. So I'm going to go through and 2 then makes it 1.008. And 3 servers makes it 0.856. And again, we come up with the same solution, but you have to recognize that that might not always be the case, right? And then this becomes 0.836. Okay, so still 2 servers is the optimal. I would also say, though, that there's not much difference between 2 and 3 servers, and so if you felt like you're competitive, one of the dimensions that you compete on is time, right? You'd be better off to go with 3 servers if the cost is not that much more, right? You'd have more satisfied customers in the long run, okay? And if you compete on low cost, then you're probably okay to think about going with the lowest cost option there, okay? So that's the infinite spreadsheet, okay? And then the next example says, but what if you don't have an infinite queue? How does that change things? Okay, and so again, our first, whenever we're using the spreadsheet, is are we in an infinite queue or are we in a finite queue? Okay, and so then example 8.8 says, suppose that LL Bean's call center is currently staffed by 1 customer service rep who takes an average of 2.5 minutes to handle a call, and that call comes in at an average rate of 20 per hour. So far we haven't really changed. We've got 1 customer service, we've got 20 per hour rate, and our processing rate is the same as what we had in the last example. Okay. However, there are 5 telephone lines. So as soon as it tells me I have 5 telephone lines, am I infinite or finite? Finite, right? So I'm going to click onto the finite. And so now I see in the finite, I'll go ahead and show the bigger picture for just a second here. In the finite, right, I have 4 pieces of information that I need to input. And the last thing that I need to input here is, so I need to input how many servers. So we said 1. What's our buffer capacity with 5 telephone lines? 4, right? Because I have 5 telephone lines, 1 of them is being used to offer service. Okay, and my arrival rate we said was 20, and my processing rate we said was 24, right? That hasn't changed from the previous example. Okay, what changes is some of the information that we get. Okay, and so the very first thing that I think is important is that average rate leaving without service. Okay, and so restate that as that's the number of people that are being blocked from the system. Okay, and so we get a percentage on that. So you have about 10% of your customers who are trying to call in are actually being blocked from not even able to get into the system. I think that's a pretty valuable piece of information to understand. And I don't know how you'd get it without doing an analysis like this, right? So if people can't even get in, how do you know, right? So statistically, we can estimate that. Okay, I sub I is still, on average, how many people are waiting in line. T sub I, on average, how much time do they spend waiting? Okay. We don't use this, so I'm not going to worry about it. I mean, you can mess with that a little bit, but we're not using it in any of the problems. And it tells us the average utilization rate of our servers is currently 75%, and the average number of customers being served is 0.7494, right? Their average time in the system, or the average number in the system and the average time in the system. So we go from, okay, what's the inventory of people and what's the inventory of, or I'm sorry, what's the inventory of people waiting and what's the average time of waiting. And then we look at the inventory of people in process, and we look at the total, right? And so if life is good, we should be able to look at these two, I sub P and I sub I, 1.229 plus 0.749, and it's going to total to the total number of people in the system, okay? All right, so that being said, we recognize that the probability of someone being blocked from the system is 10.07%, okay? And our utilization rate, again, is 74.94, okay? But as we kind of take a look at how we might analyze that, we're going to go ahead and take a look at a spreadsheet that looks at example 8.8. I'm going to go ahead and enlarge it so we can get the... So now we're interested in what's the effect of buffer capacity on the process performance, right? And so we said we had 5 telephone lines available. Here's how we calculate the buffer, right? It's the number of lines minus the servers. We have our arrival rate that we've already calculated. And so I'm going to come over here, and this comes from, right, I just copied and pasted this from our other spreadsheet. And what I've done is I've color-coded it because I think it helps you visually see where things need to go in the analysis, all right? And so we have all this information, and then down here, we need to know what's the probability that we're going to be blocked. Well, with one server, it's 10.07, okay? Our throughput is 17.99, again, given to us up here, orange to orange, okay? Average number of calls in the queue, what's our inventory there, okay? And so it's 1.229. And the average wait time in the queue is 4.1, and our capacity utilization is 0.75, right? And so we can look at that, increase the number of telephone lines, right, but not change the number of servers. And if I were to do that, and it goes away. So if I were to do that, what happens to my waiting time if I increase the number of buffers? First off, tell me what do you think is going to happen to it before we actually look at it. So conceptually speaking, I'm not changing the number of people that I have serving customers, but I'm increasing the buffer. What's going to happen to the average amount of waiting time? It's going to increase. What's going to happen to the average amount of people that are getting blocked from the system? It's going to decrease, right? Because we have more capacity for them to get in. Okay, and so again, it starts to become about kind of those trade-offs that we talked about. Okay, and so so I can just keep increasing this and watch what happens. So what should happen is we should see the probability go down. So it went down from 10 to 7.74%, right? The average waiting time is going to go up, right? And so if I add another server, right, probability of being blocked goes down, average waiting time goes up, right? And the average number of people waiting goes up. So if I keep probability of being blocked goes down, average number of people goes up, and the average time goes up. And so what I want to do then is I want to show that kind of side by side. Right? And so what I've done is we've just put that in a table, and so you can see as I get up to 10 servers, the probability of being blocked goes down to 3%, right? My throughput in terms of units per hour increases, so I'm getting more customers through, right? But the average people waiting goes up, and the average time that they wait continues to go up, right? And our capacity utilization goes up, okay? Because I have the one server, and they have more people in line they can have that line lengthens out, and so that server is more utilized than if that buffer capacity is smaller, right? But again, we have to decide, is that a good thing or a bad thing? And so we have to use some information about what's the cost of people being blocked from the system and what's the cost of people waiting, and try to figure out where's our sweet spot, okay? And so in example 8.9, so we say that suppose any caller who receives a busy signal hangs up and orders from a competitor. Okay, so then LL Bean estimates the average cost of lost sales to be $100 per customer. So that 10% that we're losing, right, it's $100 for each customer that we're actually losing. And so furthermore, suppose that a customer call gets in, each minute they spend waiting on hold still costs the retailer that $2 per minute. So there's this balance, right? We want them to come on the system, but we don't want them to have to wait too long because we're going to lose, we're going to lose out from that, okay? And, oh, by the way, each telephone line costs $5 per hour. So as I continue to add lines, it costs me more for that as well. And so our customer service reps' wages are still $20 per hour. So I'm going to shrink it, and then I'll blow it back up as we look at different parts of it. So you can see that, right? So the bottom line is, all of this information, right, comes from what we just calculated, and it comes from updating the performance.xls and just transferring that information into this table. Is everybody on board with me on that? And so we changed that information. We kept it at one server, but then we continued to add buffer capacity. So this is going to look at, well, what's the cost of that buffer capacity? How do we determine whether that's a good thing? So we take the table that we created from performance.xls, right? And we start to then summarize kind of these four pieces of information. What's the cost of our wages for our server? Well, we're only keeping one server, so that's $20 an hour, right? And what's the cost of telephone lines per hour? Well, if we have to add one telephone line, we start out with 5 at $5 a piece, go to 6, 7, 8, 9, 10, right? So we're adding $5 an hour for that. Then it's where we get into what's the margin loss due to the blocking of that call, okay? And so what we're going to do is we know that it costs, so we know if we're trying to understand how many are actually being blocked, right? We say that the arrival rate on the system is 20 per hour, right? And we know that 10.07% of them are being blocked. So we're going to take our arrival rate of 20 per hour and multiply it by the percentage of being blocked by the 10%, and then we're going to multiply it by the cost of having that customer being blocked, $100 an hour. So $20 an hour times 10.07% blocking times $100 cost for the blocking, okay? And that tells me it's $201.40 an hour at 5 telephone lines and 1 server. That's the cost of being blocked, okay? Our cost of waiting per hour is still the same as how we calculated it in the previous example, right? It's going to be, okay, well, it's $120 per hour times however many people are actually waiting in the system times the 1.23. And then the last thing I'm going to do is just sum up all of those costs to say, well, what's that average hourly cost for this combination, 5 telephone lines and 1 server, okay? And so what we can see is as we go across, okay, 5 and 1 costs us $394, 6 and 1 costs us $387, okay, and 7 and 1 costs us $391. So we would say, given this information, we would want 6 telephone lines and 1 server, right? So do you feel like you understand how to gather the information to put into the spreadsheet? Is everybody feeling comfortable with that? Because that's if you can't do that, then you can't do any of the rest of it, right? So you have to be able to understand where the information comes from. So first off, is it infinite or finite? Infinite meaning there's no queue length restrictions. Finite meaning you're given some set of queue length restrictions, right? What's the arrival rate? What's the processing rate? Okay, and then understanding how to calculate the buffer. All right. So with that being said, we can even get one more degree of complication. I know you're excited about that, right? What if I want to add servers, right? And so then basically we take that same information and we put together a table that says, well, what's the effect of the buffer and processing capacity on blocking if I have one, so here I'd have 2 lines, right, and 1 server, right? Here I'd have 3 lines because I have a buffer of 1 and 2 servers, a buffer of 1 and 3 servers, a buffer of 1 and 4 servers. And so what you do is you go through and you plug in that information in your spreadsheet, and it's going to give you the probability of being blocked. And you're just going to update your spreadsheet with that. And then you're going to go through and you're going to calculate it for, okay, what if I have 1 through 5 servers but I have a buffer of 2? What if I have 1 through 5 servers but a buffer of 3? And all we're doing here is entering that probability of being blocked. Okay? And then in that same vein, as you're doing that, you're also going to capture the information about, well, how many people are actually having to wait in the system, right? So what's the effect on the waiting line? All right? And then we set up and we do our spreadsheet, which gets a little complicated, and I'm not going to ask you to do anything that complicated. I just want you to know that you can, right? That we could look at both of those. And we would say, okay, if I'm interested in that total hourly cost, right, the first thing I'm going to do is I'm going to take 1 server times $20 per hour, right, because that's the cost of service. The next thing I'm going to do is I'm going to take the number of telephone lines, right, times the cost of the line charges, okay? And then so we had to do the cost of the line charges, then we have to do the cost of blocking, right? So it's 27.47% times the throughput rate, right, which we have down here, times 20. And I'm going to multiply that times the cost of someone being blocked from the system. And then I have to look at, okay, and what's my cost of waiting? Okay, well, we have on average 0.27 people in the system, right? Those 0.27 people cost us $120 per hour, right? And so I can sum up those 4 costs. So I've got the cost of my servers, I've got the cost of my equipment, I've got the cost of people being blocked from the system, and I've got the cost of people having to wait too long. And we've summarized all 4 of those pieces of information into this table, right? And we identify that the sweet spot is with 3 servers and 2 buffers, right? And so that's how we know that's the sweet spot. Clear as mud? So the first one should be, I mean, I think the one before that is pretty straightforward. And I'm not going to ask you to do anything where you have to do both. But I want you to know that if if at some point down the road, I've had a couple of people that have graduated have emailed me and asked me for this spreadsheet. And so I do want you to know the capability of it so that if you want to use it, you can. And I'm always excited when that happens because it means that they're actually using, what we talked about in here. But it's got to be in the right spot. Not everybody's going to use it, but some folks have had need of that, especially when you start to try to understand who's not getting into our system, right? I don't know how else you capture that unless you do the statistical analysis of it. Okay?
Is this just going to be like for our homework then?
Mm-hmm. Yeah, and what I'll do on the exam, and we'll do an exam review, but what I'll do on the exam is I'll give you screenshots of the performance.xls with the data in there, and then you'll have to answer questions based off of that. So you'll be using the information. So the exam is set up in 2 ways. The first is I give you a problem and I say, tell me what is based on that information, what's the number of servers, what's the queue capacity, what's the arrival rate, and what's the processing rate. So there's a couple of questions that are just on that, one infinite, one finite. You have to determine whether infinite or finite, right? And then you have to tell me what variables you're going to input. But you're not actually going to use them because you don't have access to Excel when we do the exam. And then the next set of problems are going to be, one will be infinite, and I'll give you a screenshot, and I'll say, calculate the cost of waiting, calculate the total cost of service, right? And so you'll need to know how to do that. And then, so there'll be a couple of problems like that. So, again, we won't do any of the complicated And it's really not that complicated. It's just, but it's time consuming, and I'm not sure the value add is worth it. I think you can figure it out if you need to use it. But that's kind of the approach that we're going to take. I do want to come to the end of the chapter here, and I want to ask some questions just to get conceptually make sure that your thought process is where it needs to be. So I'm trying to think. Julie, did you answer a question? Okay, so I'm going to ask you the first, and then we'll go to Chelsea, and then back to Blake. So a call center has a total of 12 telephone lines coming in. Okay. And they have 5 customer service representatives, and they receive on average 2 customer calls every minute. Okay. Each customer service requires on average 2 minutes to serve a caller. After great deliberation, management has decided to add another line. So they were going from 12 telephone lines to 13 telephone lines. As a result, the call center can expect what? The proportion of potential customers getting a busy signal will increase, decrease, or remain the same, Julie. So if we add a telephone line to a service operation, the proportion of potential customers getting a busy signal.
Oh, just kidding.
Yeah, just kidding, decrease. Okay. Chelsea, average flow time experienced by customers then will increase or decrease?
It will increase.
It will increase because you're going to add an extra line, and that just is an extra position for them to be on hold. Okay. Blake, average utilization of customer representatives will increase or decrease or remain unchanged?
You're adding a line.
We're adding a line, so basically think of it as you're adding a spot for someone to come on hold that couldn't go on hold before.
Increase.
You're going to increase your utilization, right? Because it's just having that extra slot just means that you get one more person into the queue that wouldn't have gotten there otherwise. Okay, so Troy, we're going to go to the next one, and I'm going to start with you. A mail order company has one department for taking customer orders and another for handling complaints. Currently, each department has a separate telephone number, and each has 7 telephone lines served by 2 customer representatives. So we've got identical departments side by side, right? 7 lines and 2 customer service reps. Calls come into each department at the same rate, 1 per minute, and each representative takes on average 1.5 minutes to serve a customer. So still identical, 2 departments. Okay. Management has proposed merging the 2 departments and cross-training all workers. So then the projected new department would have 14 telephone lines and served by 4 customer service representatives. As a process manager, you would expect the following. The proportion of callers getting a busy signal will increase, decrease, remain unchanged.
Stay the same.
Okay. You agree? Or do you know? Anybody have a strong feeling one way or the other?
Stay the same.
You all think stay the same? And so that's not right, and here's why. and that's why we're having the conversation, because conceptually what happens is you have these 2 departments that are identical, right? But they have these different, the variability that they have, right, is maybe at one time this one's busy and this one's not. Right? And so what happens when you combine them is now you're combining that variability, and it actually reduces it because you're averaging that variability across the whole set, as opposed to it's not an additive thing, it's averaging it. Okay? And so that's a concept that it took me a while to get my head around, and it doesn't seem intuitive, but that's what happens when you combine. So that's the same time when we talk about safety stock and we have multiple locations, and we say, well, what happens when we combine those into one location? You actually get to carry less safety stock because you're averaging that variability as opposed to breaking it apart and putting it in separate locations. Okay? So I'm not surprised, but that's why we're talking about it. Average flow time experienced by customers will increase, decrease, or remain unchanged. So Austin, increase, decrease, or remain unchanged?
I think it'll decrease.
You are right.
Okay.
Because if you think about variability decreasing, right, average variability is going to decrease, so therefore your average flow time for customers is going to decrease as well. All right? Now I'm going to read the next problem, and what we're going to do is we're going to try to identify whether it's infinite, finite, and what the variables are that we should use in the spreadsheet. Okay, so 8.3 says, entrepreneur John Doe has just founded Pizza Ready, which will accept pizza orders for pickup over the phone. Pizza Ready's strategy is to compete with established pizza restaurants by offering superior, fresh made-to-order deep dish pizza and excellent service. As part of his advertising campaign, Doe will publish an ad stating, if your pizza is not ready in 20 minutes, then Pizza Plus, your next order are on us. So basically, they're going to give it away for free. He's done extensive research on the pizza making process and knows that all fresh deep dish pizzas require 15 minutes of oven time and 2 minutes of preparation. Moreover, as part of its excellent service, Pizza Ready will accept orders whenever customers place them, and a marketing study estimates that Pizza Ready can count on an average demand of 20 pizzas per hour. So, he's got 5 pizza ovens, each of which is able to bake 1 pizza at a time. Okay, so are we talking, Abby, first, are we talking an infinite or finite service system?
Finite.
Because why?
He only has so many ovens.
Right. Actually wrong. I went there with you. I went there with you. It's actually, so the number of people that can call in and place orders is infinite, right? But the number of pizza ovens represents what? The number of servers. Yeah, I reviewed this early this morning and I went right there with you, Abby. So don't. I was like, yeah, that's right. No, it's not right. So we're going to go to the finite tab and we're going to say that we have basically. No, we're going to go to the infinite tab. I still want to do finite. We're going to go to the infinite tab and we're going to say that we have 5 servers, right? And did you catch the arrival rate in there, Miranda?
No.
Okay. Let me read it again. So it says that can count on an average demand of 20 pizzas per hour.
So
20, right? Okay. And so Julie, we're saying that our processing rate is we say that it takes.
It didn't take 15 minutes to cook.
Yeah.
And 2 minutes to prepare, so.
Mm-hmm.
17, or 1 over 17.
Okay, and then
That's minutes and
That's
that's an
minutes,
hour.
7 times 60.
okay, so let's do a little math here. So basically, we're saying that we're at 17 minutes per hour equals 1 divided by 17 equals this times 60. Is that what we're thinking?
Yeah.
And so basically 3.529. Okay. So let's go 20. Okay, so what does that tell you? Would you make that investment? It's telling you that you're not going to be able to get it done, right? It's saying that we don't have enough capacity to be able to do that. So then sometimes what I like to do is go, okay, well, what if we had 6 servers? Okay, well, look, at 6 servers it becomes, if we had 6 ovens, then we could actually do it, right? But then if we said if we had 6 servers, okay, what's the probability that somebody's going to, let's say, the average time, so he was going to make a bet on 20, right, on 20 minutes, that it would be done in 20 minutes. What's the average time if with even 6 servers?
Just over 20 minutes?
What's that?
Is it just over 20 minutes? No, sorry.
So it's saying that the average number in the system is 20.
Okay.
Okay. And are we in?
Hours.
We're in hours, right?
Yeah.
So basically, it's an hour. right, is the average service time with 6 ovens. So is this a good idea? No. So what we're wanting to do is then how many ovens does it take to actually get us to 20 minutes? And so 20 minutes is a third of an hour, right? So we're going to have to keep adding ovens, right? And so we get below a third of an hour. And then we can say, okay, well, on average, it's going to take that. And you probably are going to want something a little bit better than average, because average would say 50% of the time you're going to get there, right? So do you see how you can, although, Abby, I walked down the wrong path with you, you see now how we can get there with that? Okay. Let's do one more, just kind of walk through the logic of it. Listen to the logic here. So Sprout, so I'm looking at 8.4, a catalog mail order retailer has one customer service rep to take orders at an 800 telephone number. If the CSR is busy, the next caller is put on hold. For simplicity, assume that any number of incoming calls can be put on hold. Infinite or finite? Infinite, right? Nobody hangs up in frustration. One call comes in every 4 minutes. What's that? It's our arrival rate, right? One call every 4 minutes. And it takes an average of 3 minutes to take an order. Okay? So if I say one call every 4 minutes, right, I think we're saying 0.25 is the arrival rate and 0.333, one call every 3 minutes is the processing rate. Okay? And then so now and we had, how many servers did we say we had? Did we? One? There. Okay. And so all I wanted to do is read through that so you were able to get that. And I was thinking we were doing an infinite example. So let me find, I was thinking we were doing a finite example. Let me pick a finite one. Interesting. I don't think they have a finite example back there. Let's just take that one and make it a finite example, though. Okay. So we said that we knew that our arrival rate was 0.25, right? Our processing rate was 0.33. Okay. So if I were to tell you that we were working with a customer service system that had 4 operators, so what's that represent? Number of servers is 4. And that they had 12 telephone lines, what's K?
8.
There you go, right? So it's just a matter of making sure you recognize that the buffer capacity isn't the same as the total number of lines. It's the difference between the number of lines less the amount of servers that you've got. Okay, so I think you're prepped to do your homework for this one. Again, I think this spreadsheet's uber cool, but that's me. That's geeky me. And it is something that I have had multiple students call me and ask me for it after they've left. So keep it in mind if you're ever someplace. It's something that it's a tool that can be useful, and not all of you will use it. I recognize that. So. All right, with that being said, have a great weekend, right? And I will see you back here next Tuesday. It's exciting. It's supposed to be beautiful weather too, right? So enjoy, and I'll see you around.
Hey, good luck.